So we will continue our discussion on Lagrange multipliers. In the last class I introduced Lagrange multipliers. Basically it is a technique which can be used to solve multivariable constraint optimization problems. Only requirement is that the constraints must be equalities and both the objective function and the constraints must be differentiable, right. So you get to solve m plus n equations simultaneously, where n is the number of variables and m is the number of constraints. Okay, so you have m plus n variables, x1 to xn and lambda 1 to lambda m, where lambdas are the Lagrange multipliers. Through a problem we also figured out what is the physical interpretation of this lambda. This lambda is basically the sensitivity coefficient. If it is a one constraint problem, it is the sensitivity or the change in the objective function to a change in the constraint. So in operations research it is also called as the shadow price, right. If you have several constraints, the particular Lagrange multiplier, so if you have m constraints lambda 1 2 3 up to lambda m, each of these will represent the sensitivity of the objective function to that particular constraint. Okay. So in fact some people towards the end of the last class they came and asked me, sir, second time when we increase the volume of the tank from 4000 liters to 4500 liters, I am getting a new value of lambda and all that. Of course lambda will change, but the original interpretation is for the tank volume of 4000 liters, if you have a lambda, that means when you change from 4000 what is the answer. Suppose for 4500 you get a new value of lambda, that means from 4500 liters if you change to a new value, how is the area going to respond. Okay. So we will solve some more problems, and through these problems I will also introduce to you what is the physical interpretation of these Lagrange multipliers. Is there a mathematical proof for these Lagrange multipliers? How do we figure out whether the stationary point, that is the extremum we have obtained, is indeed a maximum, minimum, or we have not checked that so far, right. For if you are solving it as an unconstrained optimization problem in one variable, it is possible to take the second derivative. If it is less than 0 it is a maximum, if it is greater than 0 it is a minimum, if it is equal to 0 it is a inflection point. But I told you, somebody asked me this question, I told you that we have to look at the Hessian matrix and all that. So we will go through a very tricky derivation where I introduce the concepts of positive definite matrix, negative definite and all that, because these are all important in order that you are able to figure out whether a particular whether the stationary point you have reached is indeed a maximum, minimum, or a saddle point. Okay, saddle point is an inflection point. Now what is the problem number? 20, 24, 24 or 5? No, the tank was two problems. 24 yeah, it is a simple problem, but still let us do this. Determine the shortest distance. Determine the shortest distance from the point 0 1. Determine the shortest distance from the point 0 1 to the parabola x squared equal to 4y. Determine the shortest distance from the point 0 1 to the parabola x squared equal to 4y by a eliminating x, b Lagrange multiplier technique, a eliminating x, b Lagrange multiplier technique. So this is explain why the approach A fails, and explain why A fails to solve the problem while B does not fail. Okay, explain why A fails to solve the problem while B does not fail. So this I will give the credits. Ravindran, Ragsdale and Reclitis. So Ravindran is the author of hugely popular operations research by D.T. Ravindran, Phillips and Ravindran. Have you heard about this book? Operations research by Hamdi et Taha. That is the like Bible. It's a very good book. D.T. Philip, Ravindran, and they are all industrial engineering professors. Ravindran and Philip is also a good book. This guy, this Reclitus has done a lot of. He's a stud guy. He has thought about several optimization problems, how certain techniques can cup. He is on all those things. He has written a lot of papers about how to establish the robustness of various techniques and so on. Anyway, now the parabola is, how does it look like? Yes. Yeah, please solve. Varun Joshi, what happened? Thinking hard. Where is this 0.01 anyway? Yes. Let us say y equal to 1, y equal to 1, x equal to 2, right? Huh? Y equal to 1, x is plus or minus 2. So, I will change the scale now. Now, we are fine? No, approximately, okay. And the shortest distance is so obvious. So, the Lagrange multiplier should also give the same answer, right? What is the shortest distance? 1. Shortest distance is this, right? Are you getting the 1? You can start with B first and then proceed to A. With B also some people may get stuck. Okay, let us start with B. Minimize. Some R, I will call some R. It does not matter, right? I can minimize Z square or Z. Subject to phi equal to all right. So, using the Lagrange multiplier, lambda 1 dou r by dou y. I am writing the constraint again for the sake of completeness. So x, y and lambda are the three unknowns. There are three equations. It is possible for us to solve the three equations to determine the three unknowns. Okay, let us do the first one. Dou r by dou x is 2x. This is also 2x. Four minus 4. Dou phi by dou y. So from 6 that such a simple and stupid problem you are not able to solve.
So y equal to minus 1 is out of the constraint.
Exactly, actually, right, yeah, I think you are awake.
So what from equation 6 we get another solution x equals to 0.
Yes. That is the point. When you cancel the x, you imply, it implies that x is not 0, but unfortunately x equal to 0 is a solution, right? That is the catch in this problem, right? You cannot cancel that because x equal to 0 is a solution. So even Lagrange multiplier fails, we have to be alert. Therefore from equation 6 x equal to 0, Vikram, is it okay? When x equal to 0, now you can y phi equal to 0, therefore y is equal to 0. Now z will be if x squared is equal to minus 4 is forbidden, and as Akshay said y equal to minus 1 is outside the parabola, it is not a point in the parabola. Okay, so sometimes you have to be alert. Of course in engineering x, y are all variables, you cannot put 0, 0, 0, everything is 0 is not a, right, but I was looking at various problems, I thought this is an interesting one, okay, so I thought we will work it out. Now what about the other method is totally fails, no? You have no clue what is going on. Let us do that.
No, it doesn't.
No, that gives some z equal to 1 something. Distance equal to y plus 1.
Y is greater than 0, so y equal to
Distance equal to y plus 1. It doesn't give any more information. Let us work it out. Okay. See, for those people, for those doubting Thomases who thought that all the constraints can be put back and then you can make it an unconstrained problem, there is no need for Lagrange multiplier. This simple problem gives you trouble. Okay, so it is not always, it is not wise to convert it into an unconstrained optimization problem attempt. Even when you are attempting the full constrained optimization problem, the Lagrange multiplier can give trouble if you are not alert. Okay, let us do the A part. that is all. After this you can't do anything. No, all that is but the Lagrange multiplier method you do not have to do. Now you are intervening, right? You keep on intervening. But the Lagrange multiplier is without the intervention of the analyst, it automatically gives, because when you solve this equation x equal to 0 is direct possibility. Here now you are going to say no, y is not a point, you have to give additional arguments in order to get the answer. Therefore, this is quite inferior compared to this. Okay, so it just gives z equal to y plus 1, that is also correct, but who will give us the value of y? Which calculus? What?
Using two variables.
Here also I am using calculus.
Yeah.
No, if see, the logical thing is x square equal to 4y, you want to substitute in that equation and do it, it does not work out, that is what I am saying. This just serves to illustrate the point that you cannot convert everything into an unconstrained problem and hope to get the solution. Okay, fine. Now let us, is this clear? If there are any other interpretations, you tell me outside the class or tomorrow. Now let us do a graphical interpretation of the Lagrange multiplier method. So the methodology I would like to use for illustrating the this graphical interpretation of the Lagrange multiplier method is as follows. We will take a two variable one constraint problem. Using the regular Lagrange multiplier method, we will get the solution in 10 minutes. Let us say we will get the solution in 10 minutes, so that you know, everybody knows for sure there is a solution and it is not a fictitious problem and all that. Then I have brought graph sheets, I will circulate the graph sheets, then you will plot whatever is required, okay, and then you try to interpret from your solution of the Lagrange multiplier and your plotting, is there a correlation between these two, or is there a correlation between the equations I have given and what you are seeing on the graph and so on. Then I will sum up the discussion so that you remember for life what is interpretation of the Lagrange multiplier method. Alright, let us take a simple problem. Now I do not have to say adapted from and all that, it's on my own problem. So yes, minimize y equal to 4x1 plus 3x2 subject to of course minimize y equal to 4x1 plus 3x2, it could be minimization of some cost subject to some criterion, right. Yeah, now use the Lagrange multiplier method, do not try to convert it into an unconstrained problem, solve it as a constrained problem because we want to know lambda and other things, get the value of lambda, get the value of x1 and get to x1 and x2 are the optimum, get the value of y. In the meantime I will take attendance. Once you are through with this solution after 10 or 15 minutes, then I will distribute the graph sheets, then we will plot this and let us see what is actually going on in this problem. You can, okay. Fine. So let us work it out. So dou phi by dou x1. All right, equal to 0. 3 dou phi by 2 x1 x2, right. Is it okay? $1.89, huh? This is correct?
Yes, yeah, that's good.
X2 plus 5 point something, 5 point, y plus 6. Yeah, at this stage we do not know whether it is a minimum or a maximum. Or one possibility is to convert it into an unconstrained optimization problem in x1 and take the second derivative, or unconstrained optimization problem in x2 and take the second derivative if you do not have enough knowledge. Otherwise you can go to the Hessian and all that, which is too premature to discuss in today's class. Tomorrow we will come, instead of 10 o'clock it is 9 o'clock, so it will be better. So it is somewhat advanced mathematics, is a very tricky derivation, so we will do that derivation in tomorrow's class. But now I will distribute the graph sheets. Yes, so we need volunteers. Deepak will distribute for these 2 rows, the other 2 rows. So do not worry about y, take x1 in the x axis and x2 in the y axis, plot the constraint and then think how to solve this problem using the graphical method. Now now so the graph sheet is given to you, take the 2 axes as x1 and x2, it is better to do it on the board or using the computer. I will do it on the board. we have to organize, otherwise first 5 minutes in tomorrow's class we will do it only. So tell me the tell me the divisions. So you want x1 to vary from what? See, some 48 is coming, so you have to be smart. There are only 20 divisions of x and 20 divisions of y.
Take more values of x1 than x2.
Oh, that is that's all right, but if you are ready not to get confused, do that. You can take y axis to be x1 and this. Whatever. So you are free to explore whatever, but I stick to the conventional this thing. So what are the divisions you want? 0 to 10, huh? 0 to 10. Y x2 is also 0 to 10, but x2 is more restricted, isn't it? Because its square root is coming. Alright, so let us say 1, 2, 3. So please note that first we are plotting the constraint, okay. So better to draw up a table. One. What do you get? 6.8, huh? For x1 equal to 1. 6.9, good. Okay. 2. 4.9. 3. 4. 4. Okay. 5. 6. 2.8. Yeah. Now check these values once. It is possible that Sampath has made a mistake. So, huh? 4 is 3.5. Okay. Yeah, it cannot. Is okay. Then check these values once and then go ahead and plot. Okay, for 1, 6.9. So I have to increase this guy. So 2 is about 5, 3, 4, 5, 6 is 2.8. So it is going very or we will say got it. So some curve which looks like this, at least qualitatively. Okay, what next? You have to draw several lines now. You have to draw several lines, each of which represents different values of y. Okay, so you can take y equal to 4x1 plus 3x2, y is equal to 10. It will give one line, right? 4x1 plus 3x2 equal to 10. You plot that line. That line may not meet the curve. It's all right, but that line is a genuine objective iso-objective line. Okay, because it represents 4x1 plus 3x2 is equal to 10. Now you will say take one more line, 4x1 plus 3x2 is equal to 20, 4x1 plus 3x2 is equal to 24. But if you take 4x1 plus 3x2 equal to 22.67, it becomes a tangent to this curve. Do that, take 3 lines, do not be lazy, we have another 15 minutes, take 3 lines. Let us take y 3x1 4x1 plus 3x2 equal to 10, 4x1 plus 3 equal to 15, and do not take 22.67, take 25, so that it goes into the curve. You will realize, therefore, if you take a scale and move this y equal to c lines close to the constraint, one particular line will just touch this constraint. Okay, that is where you get the solution. Is that okay? So let us draw some iso-objective lines. We'll draw at least 2 lines. What is y iso-objective lines? Y is equal to constant. Okay, let us say two points are enough, right? Okay, so 2 points are enough. Are you able to cover this? Okay. And you thought that graphical method is simple. Lagrange is better, right? Okay, so let us take x1 equal to 0, right? X2 equal to 3.3, x2 equal to 0, 2.5, correct? So x1 equal to 0, x2 equal to 3.33, x2 equal to 0 is 2.5. That is a y equal to 10 line. For y equal to 20, so x1 equal to 0, 6.67 is 0, this is 5. Is that right? It's going off. What is the actual solution you got? Actual solution is somewhere here, right? What do you mean by actual solution? The solution we obtained using the Lagrange multiplier method.
Actually, now what we are doing is, what are your drawing are infeasible solutions, right? These are not solutions.
No, I have not drawn the. I am just trying to figure out a way of getting the solution, because I don't know the 22.67 now. Okay, suppose I don't know Lagrange multiplier method, but it's a two variable problem. I am suppose I am only, I don't know this advanced calculus, I don't know lambda and all that. I want to still solve. Okay, so how will I do this? Okay, is that fine? So, but when we move from y is equal to 10 to y is equal to 20, we are approaching close to the curve. That means we are near the answer, but not quite there. Okay, right? So, what is the procedure? What is the procedure we are trying to follow? We are trying to draw iso-objective lines, that is lines representing y is equal to constant, where this constant keeps on changing. So, we are trying to move this y is equal to constant lines, which are basically parallel lines because they all have the same slope. We are trying to move such that one of those lines becomes a tangent to the constraint. Okay, when it touches the constraint, at that point you will get the solution, because the iso-objective line is meeting the constraint. At any point on the constraint is a valid solution to the problem, because the constraint cannot be violated. Now, if you move further, again the constraint will be violated. Therefore, only if such a line, such a y is equal to constant line, where that constant is something which is the ultimate value of our objective function, that is y optimum, when it just touches the constraint, that is the solution you are seeking. Now, mathematically, what does it mean?
So, actually, if you move further, the constraint will still be met. The point of intersection, only thing is it won't be a minimum solution.
Yeah. In this case, it will be met. It won't be a minimum solution. When you cross that, it won't be a minimum, because again the y will increase. Okay. See, so which means when you are left of the curve, you can get values of y which are very low. Which, if y is a cos, you can actually cheat. You can try to cheat. You can report very low values of y, because y is equal to 4x1 plus 3x2. You can take some arbitrary values of x1 and x2 which satisfy this and say that is a solution. But your x1 squared, x1 x2 squared is equal to 48 will not be met. Okay, right? Therefore, when it exactly cuts this, that represents the minimum cost to the problem at which the constraint is not violated. Now, what does this Lagrange multiplier method do? Okay, so which means the tangent to the constraint equation at the optimum solution, at the optimal point, and the iso-objective line, they are parallel to each other. An alternative way of saying that these two curves are parallel to each other is saying, an alternative way of saying this is the gradient vectors will be parallel to each other. If the gradient vectors are parallel to each other, I am not saying that the gradient vectors will have the same magnitude, but I am saying that the gradient vectors have to be collinear. They can even be pointing in the opposite direction. Okay, so if you want to say that the tangent to this curve and the iso-objective line are parallel to each other, it is akin or analogous to saying that delta y and delta phi must be parallel. However, their magnitudes need not be the same. They can even be pointing in the opposite direction. Therefore, mathematically, if you want to say that delta y and delta phi must be parallel, but their magnitudes can be different, the only way of doing that will be delta y minus lambda phi is equal to 0, if you do not like this, or delta y plus lambda phi is equal to 0. Okay. Therefore, we are saying that the gradient vector, the gradient del of y and del phi must be collinear, vectors. Okay. But now the thing is that all? Though the directions are satisfied by this, the solution must be on the constraint itself, therefore the constraint equation is also satisfied. Therefore, del y plus lambda del phi equal to 0 is not the only thing, this in conjunction with phi equal to 0, because anyway the final solution we are seeking is a point on the constraint equation itself. Therefore, if you come up with a set of equations del y plus lambda phi equal to 0 or del y minus lambda phi is equal to 0, and you solve this set of scalar equations in conjunction with phi equal to 0, then you will get a solution which satisfies the constraint, which satisfies all these properties. So, this is the graphical interpretation of the Lagrange multiplier method. Is that okay? Fine. So, so this point is very important, right? Ultimately, this point is very much a point on the constraint. Okay. So, the test for maximum or minimum, we have a few minutes, but I think it is, you do not have to start it today, we will do it tomorrow. How to do this Hessian? Any doubts I can answer? No. Okay. So, del y and del phi must be collinear vectors. Phi equal to 0 come anyway, the final solution is a point on this. We are not seeking any solution which is not on the constraint, right? This is, but this is not so definitive. This only says that this should be in those, on the tangent, and this must be in the same direction, that is all. Okay. Anyway, the point must be on this itself. All right. Yeah, you think about it. It may be a little bit not clear now, but once you think about it for some time, it should become clearer. All right.